Okay, so we have a planet here orbiting the Sun, half the distance from the Sun that the Earth does. And it has a small moon that goes around it, just like we do. So we want to know how long it takes for planet X to orbit the Sun. We can do this in a couple of ways, but first, either way, we need to find an expression for the radius of that orbit. So the only force on it is g times the mass of the Sun times the mass of the planet over the distance between them squared. Okay, so I'll call the Sun big M, the planet little m. So F net is gmm over r squared. It's in circular motion, and we're looking for orbital periods, so I'm going to use 4 pi squared r over delta t squared for that period. And I'll solve for delta t. So delta t is going to be the square root of 4 pi squared r cubed over g times the mass of the Sun. These r's are the same in this case because the distance between the objects is the same as the radius of the orbit. Okay, so at this point I can look up the r and calculate it. I can also use a ratio solution. That's what I'm going to do because it means less plugging in of things into my calculator, which is nice. So delta t for x over delta t for Earth is the square root rx squared, rx cubed over g mass of the Sun. That's the same. 4 pi squared r Earth cubed over gm. 4 pi squared cancels, gm cancels. Okay, so I'm left with rx over r Earth to the 3/2 power. Hey, does that look familiar? Yeah, you just rederived Kepler's third. You could have just done this problem right from the beginning with Kepler's third. Certainly when there's an elliptical orbit, you have to use Kepler's third to compare two orbits, but you can use it at any time, including circular orbits, since they're special cases of ellipses. So this ratio is just 1/2. So our ratio between the orbits is 1/2 to the 3/2 power, which is about 35%. So delta t for this planet is 0.35 years, which is 129 days, Earth days. Now, to determine planet X's mass, I can't use its orbit around the Sun because it's the mass of the orbiting object cancels out. So I have to look at its moon. So what I have for the moon, it's orbiting. So we're looking at g mass of X, mass of moon, over that orbital radius squared. That's the only significant force on it there. And we know the speed and the distance, so I'm going to do my F net in terms of v. And this will be the mass of the moon, because it's the F net on the moon. And I solve, and the mass of planet X is b squared divided by, b squared r divided by g. There we go. Take a root. And we'll check the units here as we do this. 950 meters per second squared times 2.3 times 10 to the 8th meters over 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. We take the root. Okay, so we have meters squared, meters cubed in the numerator, per second squared divided by Newton meters squared per kilogram squared. Some of those cancel out. A Newton is a kilogram meter per second squared. So that's squared. We have a kilogram squared there. Our seconds squared is definitely canceling. And a kilogram with a kilogram there. Oh, there's no root. Where did that root come from? There's no root. That's why we check these things. And meter, we had a meter still left in the top. So yay, equals kilograms. That works out just great. Okay, so that's why we check these things. Alright, so 950 squared is 2.3 times 10 to the 8th divided by g. 3.11 times 10 to the 24th kilograms. So on the same order as the mass of Earth, but smaller. And how long does it take the moon to orbit it? I know I could do this with NAFNet, but I know the distance and the speed, so that's pretty easy. That's 2 pi times 2.3 times 10 to the 8th meters over 950 meters per second. So I get 1.52 times 10 to the 6th seconds, which is 17.6 Earth days.